The speed of light in a vacuum and in air is constant, and there's its value, 3.00 times 10 to the 8th meters per second, or 300,000 kilometers per second, or 186,000 miles per second. The equation that relates the speed of light, which I prefer to symbolize the frequency with a little f, because that helps me easily remember that it stands for frequency. But on some equation sheets, frequency is symbolized by not a v, but this lowercase Greek nu, which looks a little bit like a v but isn't. Speed is frequency times wavelength. Albert Michelson, pictured in the lower right here, was the first person to get a semi-accurate value for the speed of light in the late 19th century. Here is a picture of his setup. It is not to scale, and it involved a rotating octagonal mirror, and 20-some miles away another curved mirror and a flat mirror, and the trick was you had to rotate this octagonal mirror at the right rate so that the source of light, which is at the top here, would hit this mirror, move to the right 20-some miles, hit the curved mirror, hit the flat mirror, hit the curved mirror, come back and hit this octagonal mirror, and then we could see it through this viewing telescope. And the rate of rotation coupled with the distance allowed Michelson to come to within 99% of the current accepted value of the speed of light. Pretty ingenious experiment. In 1900, Max Planck assumed that energy can be absorbed or released only in certain discrete amounts, which he called quanta. Planck assumed that energy only came in certain amounts, and he called these amounts quanta. It's kind of like if someone asks you how many cousins you have to reply with an integer number. Those are the only allowable values. You can't respond that you have 17.8 cousins. It's not an allowable number. Similarly, if someone asks you to pay for this gallon of milk that you're buying, they're going to ask you some amount of money down to the nearest cent. They're not going to say, oh, well, that gallon of milk is $3.53.5, because we don't buy gallons of milk in half cents. It's not allowed with regard to a supermarket. Planck assumed that light also came in discrete chunks, that there were certain allowable values and any value in between was not allowed. Later, Albert Einstein dubbed a light particle that carried a quantum of energy a photon. The equation that relates energy to frequency. Notice here that frequency again appears in two forms. It could be the lowercase Greek nu, or it could be the lowercase f. And of course I prefer the f. E is the energy of a photon in joules. That's the standard SI unit for energy. H is what's called Planck's constant, which is this number here, 6.63 times 10 to the negative 34th joules times seconds, or joules per hertz. Since a hertz is a seconds to the minus 1, joule seconds, or joules per hertz, are the same unit. Mr. B, I forgot. What are the units for frequency? Students typically remember the unit for velocity, meters per second. They'll remember the unit for distance, which is typically meters. For time, they'll remember it's the second. Students occasionally forget what the unit is for frequency. And whenever I get this question, as it says in the upper right here, I has a sad. Because students have no idea how much that hurts. I mean, that really hurts when students forget what the unit is for frequency. They just really have no idea how much that hurts. Let's try an example problem. A radio station transmits at 95.5 megahertz, would be FM 95.5. Calculate the wavelength of this light and the energy of one of its photons. Just for your information, FM radio stations transmit radio waves from their station out into the atmosphere at so many millions of hertz, megahertz. So 95.5 FM has a frequency of 95.5 megahertz. So here's the equation that relates speed of light, frequency, and wavelength. Well, we want to find the wavelength. Since radio waves are a type of light, they therefore travel at the speed of light. We simply here need to take the speed of light and divide by the frequency. Now notice what we've done here. I wish someone had showed me this when I was in high school. Instead of worrying about putting this denominator in proper scientific notation, which it is not right now, look in the problem statement. You see this SI prefix mega? Mega, we should memorize, means times 10 to the 6th. So what we can do is we can just take that mega prefix and throw it out and put the times 10 to the 6th right in there, just like we've done in the work for this problem. The fact that it's not in proper scientific notation is certainly not going to bother your calculator. So you can simply type it in that way using your exponent key and you'll get the right answer, which is about 3.14 meters. That's the wavelength. The energy of one of these photons, we're going to take Planck's constant and we're going to multiply by that frequency, and there it is again, 95.5 megahertz. Energy is of course in joules. 6.33 times 10 to the negative 26th joules.